Yay, more logistic growth. We could be baking or cooking something good, but no, we get to do logistical growth. So what we're going to do in this video is take a look at how curve sketching, what you know about the old first derivative, second derivative, number line, and so on, works its way into logistic growth. And so you can see pretty intuitively how that would be the case because my population graph in a logistical growth situation is very curvy. It looks like it's always increasing. Looks like we've got a point of inflection from concave up to concave down. And rarely have we, not rarely, so far, we have never been given an actual equation for the population graph. All of our logistic growth questions have evolved from being given a growth rate differential equation, the old dp/dt. And you may or may not recall that if we graphed the dp/dt as we did in the very first video, we get an equation that looks something like this, or a graph that looks something like that. And these two should be talking to each other, as we talked about, always increasing, derivative or growth rate always in positive territory. Increasing the greatest, growth rate is at its greatest. Small rate of increases, small but positive values on your dp/dt. And you could even think a little deeper and think about the derivative of dp/dt and relate it to that. But let's save that for a moment. So we're going to take a look at two common questions that could happen. And they're actually both the same question. The first question says, when is the population growing at the fastest rate? And the second question is, what is the population when the population graph has a point of inflection? Well, the reason they are the exact same question is, this is the point of inflection of the population graph, but it's also the spot where the growth rate is the most rapid. So the point of inflection of your population graph is also when the growth rate is the greatest, which is also the maximum of your dp/dt graph. Going back to this, I put an asterisk by when. When is the population growing at the fastest rate? That's actually bad grammar because I should say, what is the population when the population is growing at the fastest rate? Because our variable in play here is the p. You notice that we don't have any t for a variable. The whole thing is happening with respect to time, but p is the only value that we could get. So I really should have stated that as, what is the population? So let's work through this example. Remember, we're answering both of those questions at once. And here's the equation that I've been given. It's conveniently in a form that I like, or is it? In this case, I have to use my algebra trickery probably to go back to here, so I get to use power rule when I do the derivative instead of doing a product rule derivative. All right, so now big picture for a moment. If I want to know when the population is growing at the fastest rate, I'm actually thinking of something pretty deep. A population is growing at its most rapid rate when the dp/dt is at a maximum. Hey, this is my dp/dt. I need to find out when this thing is at a maximum. So to do that, I just pretend this is kind of like an original function, and I go through the curve sketching process. First derivative equal to 0, first derivative undefined, number line, test points, all that. Well, just remember, the first derivative of a derivative is a second derivative. So we're going to need to go down to a second derivative. Keep in mind, this is acting like a first derivative because it's the first derivative of my growth rate. Now, here's a big time problem. With all the chaos going on, you might forget that this whole thing is with respect to time. But when I take the derivative, this is simple power rule, but I just took the derivative of a p term. This whole relationship is with respect to time. I have to remember, I have to take the hint from the context of the problem that my derivative is with respect to time. That's a very sneaky form of implicit differentiation. All right, so now I really have my first derivative, if I want to think of it that way, and I have to set it equal to 0 and set it equal to undefined to see what's going on. Well, what I did here is I took this dp/dt and factored it out as a GCF. So there's a GCF going on there. And remember, the GCF is the most commonly forgotten factoring technique in America today. But this is really nice because if I take this and set it equal to 0, because I'm honoring my curve sketching, I'm saying when is the first derivative 0, when is the first derivative undefined. If I set this equal to 0, something really nice is going to happen. My growth rate in a logistic growth situation can never equal 0. To kind of get that, just remember this. We've started out with very tiny growth, and we end with very tiny growth. But technically, we're approaching an asymptote. We still have a positive slope. It's just really tiny. So if my growth rate can never equal 0, but I need this whole thing, contraption, to equal 0, that means I just need to know when does that piece equal 0. And I take that piece, set it equal 0, get a value. That's my only critical value because this first derivative, where is it? This first derivative is never going to be undefined. There's nothing about this that'll make it undefined. So that goes on my number line. I do some test points. Remember, when I do my test points, I have to plug it into, in this case, the second derivative, which is really acting as the first derivative of my growth rate. So it turns out that I have a maximum growth rate at 150 because the growth rate was increasing and then the growth rate was decreasing. So then I would go ahead and justify that. Let me arrange this a little better. Okay. The population is growing at its most rapid rate at p equals 150 because blah, blah, blah. There's the AP justification for the lawyers. But keep in mind, we were also answering this question as well, because as I showed you from the graph, a population growing at the fastest rate is also occurring at a point of inflection on the population graph. Well, I would be doing the exact same thing, and I would just come to a different conclusion. This thing that I did was the second derivative of the population graph. It's also the first derivative of the growth rate graph, or of the growth rate. But the second derivative of the population graph switched sign, and so I had a point of inflection. I got a little cumbersome there at the end. So your curve sketching skills are going to show up in logistic growth, and conveniently for you, it's pretty easy to see that relationship by looking at those graphs. And as another bonus for you, and by you I mean the people who are going to do your homework, there is a secret fact you may or may not be picking up on, but if you do your homework tonight, you're going to find out that secret fact that you can pretty much memorize, but you must be prepared to support it with the calculus. That secret fact is one thing that will really help you save time on an AP test. See ya.